Hi, welcome to my channel, The Machine Learning Engineer. In today's video, we continue with the series I'm doing about computer vision, and today we are gonna see a very interesting topic with the name steganography. This is a really ancient technique or art of, as you see on the screen, concealing messages, usually hiding secrets in a container. In old times, these containers were physical containers. Today, the container are digital containers. Today, we are going to see how to hide secret information inside images, and well, this way nobody except you and the receiver of the message and the person who you have to instruct how to extract the information from the message is going to be able to extract that information from that specific image. Today we are going to use image. Theoretically, it's possible to use other containers like audio or video to hide text, even files. You will see both today in the video, how to hide a text and also a complete file inside the images, and using in this case OpenCV as a main technology together with Python. The steganography, as I mentioned, is the practice of hiding messages, a file or message inside or even an image or file. So when I say file, is whatever. It can be an image inside another image, or an image or video inside a video. So it's hiding information in another file. Today we work with digital containers. In the past, the containers were physical containers, or even the human body was used to hide the messages in the old times. Today, as I said, we use digital containers, and these containers, as I said, it can be any. In this case, any that not any. You cannot hide information easily in some containers like a document, no? But it's also possible, believe me. But in this case, we are gonna use an image to hide messages and even a file. As I said, the technique is very old. The first documented case of steganography was 500 before Christ. So it's a really old technique. Now it has been sophisticated or changed across the time, just to use what was available in the time that was used. No, this has been used for armies, governments, spies, hackers. Today, everybody is using these or similar techniques in order to hide the messages to the height of the human being, and just to make some information get the appropriate hands, and only the appropriate hands be able to decipher or decode the message inserted, in this case, as you will see in images. Steganography comes from the ancient Greek. Is a composed word. Steganos means hidden or covered, and graphe means written. And that is today I will show you how to do this easily in Python, and using computer OpenCV, just to handle the images and iterate. So one of the most important, I have prepared a notebook before to later on I will upload to the repository, and you will be able to review in your local environment. And to understand how this works, the first thing that we need to understand is how is saved or saved or storage an image in your hard disk, or how the software, in this case OpenCV, work with an image. How is the representation of an image physically and how the is represented in numbers, in binary, what is the structure of an image, and how we can work with that in order, and how we are going to insert this information inside the structure of an image, and the eye will not be able to notice that you had some hidden information inside that. To do that, the first thing, as I said, you need to understand how the image is composed, what is the structure of an image, and essentially, for those that are familiar with Python, I suppose the most of you, if you are following me in this channel, you know that I used to code in Python, and then when in Python we to work with this kind of structures, we use the libraries like Pillow, OpenCV, or NumPy. At the end, an image is not more than an array with a shape, and inside the array there is positions that represents physical location of the pixels of the image. When you read an image, the structure is always starting in the top left corner, where you have the coordinate 0, 0. The image is structured from left to right, and from right, so from top to bottom. So here you had the coordinate 0, 0, and here you had the maximum length and the maximum height of the image. Additionally, you have an image of three of color. You have 3 channels per pixel. So the red RGB is the nomenclature, red, green, blue. So a pixel is a container, a triplex, a tuple with 3 positions, 1 positions per channel in the RGB nomenclature. So every position in your top tuple is a number, an integer 8, meaning that you had 256 numbers available, meaning that you had in total around about 16 million, a little bit more, different colors or possibilities per pixel. So a pixel at the end is a triplex, a tuple, with 3 numbers in the scale from 0 to 55, which represent the color in the 3 channels available, RGB. So the pixel 1 is this position that you have here on the top of the matrix with the number 63, 65, 60, 67. Doesn't necessarily need to be that, but well, it's just an example, and then every pixel had the same follow the same structure in the image. The image at the end, as you can see here, is not more than a matrix with 3 dimensions, which are represented by the length, the height, and the number of channels. There is some formats of images that have a channel number 4, which is the like PNG. In this channel is just used to tell you which quality, how the quality of the pixel itself, but it's not changing essentially the color in the scale of RGB. It's just a channel which a number which indicate you the quality of the color in that specific pixel. So this 4 channel or some formats, image formats, we don't use it in steganography. We just use the 3 main channels. Case that we are working with color images. If you are working with black and white images, you just have 1 channel, but the numbers remains in the scale from 0 to 255, which is essentially an integer 8 integer, which is the number which make us possible to represent 256 different possibilities. And then in steganography, we apply a technique, the most used technique. The simple one is the least significant bit. What means that? So the pixel, as I mentioned, you have here this example in the picture, is a picture of 5 by 5 pixels, so 25 pixels. Every pixel is a triplet with 3 numbers, and then changing the less significant bit means that vary slightly one of the bits of the pixels. It will allow you to insert a piece of information in that pixel, but it will not change the color that the human eye see fundamentally. Essentially, you will not notice anything. And then this allows you to insert information following a method, following a logic, changing the less significant bits in each pixel. It will allow you to insert information in the image without the human eye notice that there is any change on that. Moreover, it's practically impossible to anybody figure out that the image contains information, because usually what you transmit over the public channels is the image with the message, and then you don't have the original to compare. You will see here in the example that the original and the image with the message inserted, and you will see that there is no difference. But even in the case that you send the image using public media, you put the image in a public website, or you send the image via WhatsApp, YouTube, Facebook, whatever, nobody knows, nobody saw the original, so it's impossible to detect or to anybody understand that this image contains a message. The only person that will know that contains a message, a text, is the person to who you send the mechanism to extract the information from that message. And this is had to be agreed beforehand, because there is no material way to understand that an image contains a message if you don't know, or the person don't know, that it was inserted a text inside that. And you will see, once I explain how it works, you will see what I'm talking about. So I will see how this, with a small example, how this essentially works. So here we are going to encode the message hi inside an image of 3 or 4 by 3. And then you will see here, this is just an example, the representation of some colors in the image. No? There is a triplex, a tuple with 3 positions with numbers from 0 to 255. And then on each number represent the color in the RGB scale. And then on this is 225 in red, 12 in green, and 99 in blue. When you mix these 3 scales in the RGB, you get a color. And then on what means modify or insert high in the in this piece of information. So what we're gonna do is we translate every single number we had in per channel and per pixel to hexadecimal, and then we translate as well the number the text to hexadecimal. High in hexadecimal is this text that you see here, and then on you can apply this in groups of 1, 2, 3, or 4 bytes. So you apply the steganography just 1 byte, you are gonna change you are gonna take this the first position of this message in hexadecimal, and you will modify this. You will change the less significant bit of this channel, or the red channel. You will change the 255 with the hexadecimal representation. You will change the last the least significant bit with a 0, and the output is 224. Let me give you an example. We have the calculator here, so we are going to put in decimal 225, which is in binary 11100001. So if now we replace this hexadecimal binary number, we replace the less significant number, which is a 1, with a 0, we get the 111. So let's remove this 1110. So it's 111. Sorry, is sorry. Let me remove this. Is 1110 0000. You remember 225 was 1110 0001. We replace the less significant number with a 0, which is this one, and we get 224. This is the encoded bit. Now we take the number 12. Let's move the number 12. We remove everything. Decimal 12. In binary is 1100. If we include, if we change the least significant number with a 1, we get the number 13. So let's try out. Binary. So is in binary 1101. We get a 13. Okay. Now we go to the number 99. We had to replace the least significant number with a 1. Let's do it. So the number 99 in binary is this one. If we replace the latest with a 1, we just get the same number. You see the logic here, right? You can apply this. Here we are encoding with just 1 byte. If we encode with 2 bytes, what we are doing is simply to this number, 225, if here we have a 0, we rest 2 bytes. If we had a 1, we add 2 bytes. And so on and so forth. So if you increment the number of bytes to encoding, the change is bigger. And obviously the image is going to be more, let's say, transformed. No? So the recommendation is use 1 byte. It is possible to use. When you are applying 2 bytes, instead to use 1 by 1, you take 2 by 2. You group this and you apply to each significant number. So the way that you encode is gonna depends on how many bits you decide to use. Typically, it's just 1, and the length and the size of the image that you are working on. The biggest the image, the most possible amount of information you will be able to encode inside the image. Essentially, when you are encoding, the most simple way to do it is encoding starting from the beginning, left, right, and top down. But this is only a convention. If you design an algorithm, we are going to use today this, the simple one, but you can use create an algorithm that to do more difficult to detect. Even it's impossible to detect practically, but you can even make it even more complicated. No, you can just say, instead to encode sequentially every bit from left to right, from top to down, you can just jump one or two and not encode, for example, two bits in between. So encode the bit 0 and the bit 3. 0, 1, 2, 3, and then on follow this example. This is something that you can do. It's just programmatically you can prepare that. You are the only one that know how it's encoded, and you can pass the correct client or the correct decoder to the other person who is going to receive the message. So as I mentioned, this is practically indetectable, and is very, 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 or practically impossible to detect from somebody who never ever saw the image. We will see this in practice in some second. So I hope that this is clear how we are encoding, how we are modifying the pixel, as you can understand. So in 225 by 225 by 225 is in total 16,581 different possibilities of colors per pixel. Just going up or down, imagine the difference is practically unnoticeable. It's impossible to notice. Oops, I don't know why this appear here. Well, okay, let me. Okay, yeah, something. Okay, I will fix it later. Okay. Yeah, exactly. I just attach here. This I'm going to remove it. Sorry. Okay, this is there, and now we just simplify. Okay. Let's go to the practice. I just prepared some code. We are going to start first of all with encoding a small text in the image. I have prepared here some logic. We are going to use one bit here to encode, and then how do you know when the encoding finish? Okay, by convention you decide how to do it. At the end of the secret data, we are just adding a mark which tell us that when we get this mark, when we are decoding the image, we understand that the text that is inserted in the image is finished. Here, when we encode the image, we just open it. Here, open it with CV2. We get an ampere right. We calculate the number of the possible bytes that we can hide inside the image, and we decide which ending mark we want to use. The same ending mark is the one that you are going to use to decode the message. Here we use 5 equals, but you can change this with whatever, even with a text and not the message or whatever. It just has to be the same for encoding and for decoding. Here we apply the mechanism I showed you before. We transform every pixel, every part of the tuple to binary, and then we change one of the binary according to the hexadecimal representation of the message that we are encoding. In the decoding phase, we open the encoded image, and we do the opposite. We just using the convention that we apply here is 1 byte. We extract the byte, and we just concatenate in 8 positions, and then we translate from these 8 positions, extracted from every single component of the tuple of every pixel. We transform this into a chart, and once we get during this loop we get 5 consecutive equals, we understand that we got the end of the encrypted message, and this is what we return. We are going to do an example here. Let me So this, we open this dex PNG, is this image, and then we are going to encrypt. Here you had the shape. The shape is 1009 by 1900, o sea, 1009 from by 1900, 3 channels. This is the shape of the image. If you make the calculations, the same that we have here, total pixels, this is how we calculate, is the shape, the height by the length by the height, multiplied by 3 channels, and divided by 8. 8 is the length of a chart representation in the ASCII table. So here we had available 1,917,000 pixels to encode information, and in this case we are gonna use practically nothing. It's very short. Practically this is like 20 pixels. We will in 20 pixels we will hide this information. So we put this is the output image, and then we encode the image and we write it down to the DIX in this DEX encoded PNG. We encode it already there, and you have here the image. So somewhere here in the top left corner is encoded our message, but as you can see, nobody can even notice that something is there. And again, we are going to send this image, the disencoded PNG, to the recipient, to the receptor of the message, and then you are not even able to compare with the original one. So nobody knows that something is here. So now we use the code, and we you can see here that the code is transcribing or extracting the information from every single bit, and we just print the decode data. We open the output image, which is the DEX decode PNG, and once it's done, we will print out the encrypted message. This is a top secret message. Now we are going to do the same, but instead to encode a message, we are going to encode a whole file. We are going to take the sample PDF, which is this file. Sample PDF is a PDF. You can do with whatever file. So far you have enough pixels to hide the information. You can use whatever, a video, a picture, another picture, whatever. Just try in your local environment. I just decide to hide this PDF, and then on here we do this logic a little bit more sophisticated, and we are gonna use an arbitrary number of bits to encode. You can use 2, 3, 4, whatever. We are going to use by default 2. We don't modify this. You can review, it's exactly the same, but only we are just simply using an arbitrary number. So instead to use 1 byte, we use n number of bytes. As I mentioned you before, instead to use to take 1 byte by 1, we take groups depending on the number of bytes that you choose on the parameter. If you choose those with 2, we will take 2 bytes, and then we will modify 2 bytes into the first byte. This means that we will follow the same logic. If there is a 0, we will change by 0 the pixel in 225. If you remember 225, if we apply this case 225, let's do it again. Applying 2 bits encoding, let's write here 225 decimal, we write 225, we transfer to binary, is this one, and then on, if we use 2 bytes, we are going to change the last 2 digits with 01. So what is gonna change? Nothing, the same number. If we apply 2 bits, it's gonna be this pixel, this component of the pixel is not gonna change. The second one we take is 12. Let's change it. 12 in binary is 1100. It will change. We will change the 2 less significant bits, so 00 with 10. So this means that instead to be a 12, it will be a 14. Let's change it. Just test it. We are gonna use binary, and then it's 1 and then on now 10. So we will have a 14, and then on you will see that the number, instead to be the original pixel, will be is 255 1299, and the pixel, the encoded pixel, it will be 225 14, and the less is gonna be 99 in decimal. Let me change it. 99, sorry, in binary. So we change the less significant bits with 10. So we, instead to be a 99, it's gonna be a 98, because we removed the last one. It's gonna be replaced with 10 0. Sorry, 2, exactly 10 0. Okay, and so on and so forth. So the final the encoded bit using 2 bits is gonna be, in this case, 225 1498. And then again you will see now that this is completely impossible to detect this by the human being, by the human eye. Let's go to the code. Here we have our encoding, decoding using the same. So we have now a parameter which allow us to take instead 1 and arbitrary number of bits. We take our sample PDF, we open in binary. You can take a look to the format PDF. This is our output image. This one with file, and this is the input. This one file. This is this one. This image. And then on, we are going to encode. So here, this is the initial execution. We had 11 millions of pixels to encode. The size of the file is 272 bits. So we had to modify these pixels in the image. So we encode the image and we save the image in this test with file. And now you can see. Be attentive to this part, because the message is here inside. You will see that there is a small, it's practically indented table. You can notice that there is some changes here. You will see this better in your computer when you try this in local. But again, you are going to send this image, the image with the message, and nobody saw this image before. It can be a picture with you and your wife, or you driving a car, and then nobody saw this image before. This just contains an image, and the only person who knows that there is a message inside is the receptor. Now we are going to decode PDF. We use the same number of bits, because it's not the method will fail decoding. And here we are going to receive the decoded data. We tell that we, instead to receive the text, we receive bytes. And you can see here is a byte array, and it's exactly the same that what we had there. Now we save this into, oh, sorry, I have it open it. Let me save it. And now let me open the file, is PDF, the code, and this is here. PDF sample and PDF the code. And you can test the images. So if you check the images, obviously desk 1 and desk 2, they had different size, but again, you only are gonna see this. You're never gonna see that one. You are gonna see this, and the receptor will see only this. So again, there is a small differences here, but you can notice that because you have both. It's impossible to see. Okay, that's pretty much all. As you can see, it's a very interesting topic. We are going to see other topics connected with cybersecurity and with these interesting techniques of how to use ML and AI to do something different. We usually work with bots, generative AI, machine learning, MLOps. Now, this is a little bit different, but it's also an application of the kind of things that we do in the channel. And that's all. I will upload now the notebook to the repo, and you will be able this way to test it in local. It's, in my opinion, quite interesting stuff. And well, I hope that you find it interesting and useful for your job, for your training, for whatever reason are you watching these videos. And if so, just give me a like, subscribe to the channel as you didn't do it before, and make comments, share with your friends and colleagues. And you have the super thanks, all this stuff available on the channel. This way you will help me to grow in YouTube and continue doing this stuff that that I'm doing with passion, but it's also something that demands a lot of time from my side. Thank you very much, and see you soon.